All right, so with the introduction out of the way, let's move on and talk about the speed associated with this locality thing. So what did we just see? The point of the intro was that by locality, if I kick a charge, there's going to be some signal that moves outwards and updates everybody to the new location of the charge. So out here is the region where the electric field doesn't know the charge has moved. Here, you know the charge has moved, and then there's a little signal that updates it, and that moves out somehow. So the first thing you should ask when I say there's some, signal that gets sent, you should ask, how fast does it go? What is the speed of that signal? So let's try to answer that question. The signal speed has to be baked into whatever equations describe electromagnetism. So as it turns out, we'll meet in Act 2 these equations called Maxwell's equations that tell you all about how the electric and magnetic field behave. So if there's some speed that describes this signal, it must be somehow hidden in Maxwell's equations, because Maxwell's equations have all the information about how electric and magnetic fields work. So for now, all I want to tell you about Maxwell's equations is they have two numbers in them. So one is called the electric constant, one is called the magnetic constant. We use these letters, the Greek letter epsilon and the Greek letter mu for these constants, and they're just some numbers. So these are some fundamental constants. So there's some number, and it has some units, and some number, and some units. And if you're unfamiliar here, these letters mean M is like a meter, which is a unit of length, S is a second, kg is a kilogram, and C is a coulomb, which is a measurement of charge, the amount of electrical charge. So now we ask the question, how could we guess a speed using just these two numbers? Whatever speed there is that describes the signal has to involve only those two numbers. Well, before answering that, let's do a simpler example. Let's play some games with units. If you forgot this equation that distance equals rate times time, you could kind of figure it out. So if you wanted to know the distance you go if you travel at 60 miles per hour for 2 hours, you can kind of look at the units. 60 miles per hour to get something with units of miles, well, we have to kill the hours. So you multiply by something with units of hours, the hours cancel, and I'm left with something in units of miles, which is distance. So the only equation that will give you something with units of miles out of this rate and this time is this equation, distance equals rate times time. So you can figure out the equation purely by the units. And this is called dimensional analysis. It's a fancy name for a very simple idea of playing games with units. So now let's apply that idea to guess our signal propagation speed. So if we take these two numbers, epsilon naught and mu naught, I'm going to try to combine them in a way that gives me a speed in, say, meters per second. So the first guess would be to multiply them. If you multiply them, some nice things happen. These kilograms cancel. These coulomb squareds cancel. This meters cubed in the bottom turns into a meter squared when you kill this meter up here. And you're left with some number times second squared per meter squared. Now we want something with units of meters per second, so that's not quite right, but we can fix it. If you first take 1 over this thing, taking 1 over this thing flips the numerator and denominator, so now that's meters squared per second squared. And then you want to kill the squares by taking a square root. So if I take the square root of that whole thing, which gives me this expression, 1 over root epsilon naught mu naught, that has something with units of meters per second, and the numerical value you might recognize. This is the speed of light. 3 times 10 to the 8th is approximately the speed of light. So this is a remarkable result, actually, because we just started with some numbers that describe electric and magnetic fields, and the speed of light popped out. So Maxwell noticed this in 1864, and at that time the speed of light was known, it had been measured, and he noticed that this number agrees with the speed of light, and he said that this agreement of these results seems to show that light and magnetism are affectations of the same substance, and that light is an electromagnetic disturbance propagated through the field, according to electromagnetic laws. So the upshot is that visible light, or any other kind of radiation, radio waves, whatever, it's exactly this disturbance in the electromagnetic field, which we saw before, this stitching, when you move a charge, this stitching that propagates out, that's exactly what light is. And it moves at this speed, 3 times 10 to the 8th meters per second, which we know from measuring the speed of light, and it happens to match this speed coming out of Maxwell's equations. So that's already pretty nice. We got a lot of mileage out of dimensional analysis, so that's very cool. But Maxwell himself didn't just do this dimensional analysis. So he wrote down some wave solutions to his equations, the Maxwell equations, to prove that there are these propagating light solutions that move at the speed of light. So I want to just give you kind of an overview, skipping some of the details, but just to give you a picture or a flavor of how those equations work. So that's what we'll do in the next act.